really am very privileged to be talking about a topic which has actually, the background to this has already been laid out by our previous speaker, Mr. Pandit. So I think it makes my life a little bit easier. I'm going to talk about the sustainability or the green principles applied to medicinal chemistry. What I'm going to talk about are two areas in the health, particularly in health, the medicines and the materials. And we all know that as the population increases and the rise of the living standards are on the upward front, both demand materials. One is medicines, other is materials. And as elaborated by the previous speaker, sustainability becomes very central to the human's ability to live on this earth. The material world is dependent upon chemical resources all in between earth. So you require materials for both, whatever, in fact, anything which is in the room is a material. Now, many of these materials are manufactured by using very energy-intensive manufacturing processes, and many of these things involve petrol-based products. So now, what is important in the current context is how to replace these materials, the petroleum-based products, with renewable one, and also how to limit the supplies by there are many elements which are in short supply, particularly those which we use in mobiles, etc. So in all these cases, chemistry will play a very vital role. Now, I'll focus only on the medicines. Medicines are of two kinds. One is small molecule drugs, medicines which we all take, and the second thing is biologicals. There are distinct differences between these two. Biologicals are produced by living organism, high molecular weight, they're strongly process dependent, unstable, immunogenic, whereas small molecules have advantages in certain respects. They're produced by chemical processes, well-defined structures they have, they're process independent, categorizable, stable, and non-immunogenic. Now, what is important is the economics. When we all take medicines, economics become important, how the costing is done. The second thing is access. The small molecules are very easily accessible than biologicals because that takes a lot more process development for the biologicals, they're more expensive. There is also a disparity in the way in which they work. Small molecules, the mechanism of action are different. The cost is important thing. Small molecules are less expensive than biologicals. So access to a big macromolecule is often more difficult than access to a small generic medicine. The preparations also is difficult. Preparation of generic medicines is not a high margin business, several business models are there. Chemistry of drug manufacturing is different for biologicals as well as for the small molecules. Small molecules use extensive use of energy and solvent, and they generate vast amounts of waste, and it is far from benign and sustainable as was told by the previous speaker. Now, the drug approvals, every year more and more drugs are coming up, as you see since 1912 or 20, the drugs were coming, but in the last 10 years or so, they are on the rise, they are uniformly increasing, and we have both small molecules and biologicals both coming as drugs. And there are several drugs for different areas. Small molecule therapeutics is a very big area, and number of drugs and therapeutic classes and the countries for approval also is shown in this year. You see, in the last 5 years, the new molecules which are coming up, they have actually become, constant. In this one, India stands somewhere in the field. We are not put very, very unique drugs in the market compared to other areas. And in terms of generics by market share, cardiovascular is the one which requires a huge amount of the incidence is increasing cardiovascular, but now the nervous system, neuro-related diseases are catching up. So it's very, very important. Okay. Now, if you look at the drug market, 2025, you may not be able to see, we have something like $468 billion, which in another 10 years, it will almost go by another 1.6 or 1.7 times. One is because more and more drugs are required. The second thing is the large number of patents have been getting expired, so people are getting into the manufacturing thing, and many initiatives by governments to make health across thing, that is also another reason. The market share by different regions, I will skip the next two slides, and straight away go to statement saying that irrespective of all macromolecules which are coming up, I work in the nucleic acids, and nucleic acids are now coming as a very big drugs, peptide-based drugs, but still, small molecules medicines will be the bedrock for our medical system. Because majority of the prescribed medicines in all countries, across countries, the small molecules, they are very, very important. It will continue for years and decades. It's not going to completely replace the macromolecules because of cost, production, etc. Though new compounds are being approved by FDA, the number of small molecules, they remain same. And many important medicines, many of them what we take today, they were not discovered. They are discovered in the last, middle of the last century, even later. And the synthesis which is being followed that reflects the chemistry which was available at that time. And in the context of green chemistry, sustainability, things which we now talk, the change is now needed in their production. Starting materials come exclusively from petrol-based. Bulk of important medicines result from old chemistry, which is based on fossil fuels. And most companies, they don't make any drug from the scratch. They always outsource the intermediates, starting materials, etc. And the global supply of drug intermediates depends on many of the tiny factories that prepare specific intermediates. They do not take all the things into consideration. And given the geopolitical effects, we never know how these supply of these intermediates and APIs, they will change because of the politics. So what is important is to keep a track on the so-called supply chain. Supply is coming from different countries, different sources.
Technology-based business.
So the global supply chain is very, very important. And if you want to switch over to the sustainability, even one has to go back and change the petroleum-based chemistry and those molecules level. The chemical feedstock initially was coal tar to petrol 100 years ago. Now we need to shift to the bio-based and renewable stock. Now, this is where the organic process research and development chemistry becomes very, very important. We have professors from ICT here who have tremendously contributed to this area. Now, the thing is, this process research and development, although we all do some bit of chemistry in the laboratory, it is neither formally taught in many universities or even practiced in universities, but is almost exclusively practiced in industrial laboratories. So there is a growing disconnect between perception of challenges in academia and what is necessarily important for industrial process research, and that has to change. And shifting to the biomass products, industry alone does not have the skills to drive the shift from petrol-based supply to bio-derived starting materials, and this is where the academics will come into picture. Discovering sustainable reagents and reaction conditions for a large set of transformations is not easy, and we need to find catalysis-based, particularly the first row transition elements, because they are still available in abundant amounts in our planet, and both are needed for the transformation towards sustainability. Now, we all know about the 12 rules of green chemistry. The academic world should embrace, which is already doing with great challenges today. Now, what we require is, after 25 years of this green chemistry which is being practiced, for us to see how much it has succeeded. Now, we need to reflect on its success, and we also need to think about, does it require an update of the 12 principles of green chemistry from today's perspective? That's what I will tell you in the next few slides. And also, we talk about sustainability, green gas emission. We need to develop a strong foundation for how to do them quantitatively and quantifiable measure for sustainability. Now, the three principles, these things we have just published in one of the research articles in OPRD. One of them is understanding the supply chain. It is not just easy that you concentrate on the green process within your factory, but you must understand the synthesis of an API going back all the way to the basic starting material, which is made either by steam cracker, fermentation product, etc. And you must include the real, sustainable and estimations. You must include the reagents and catalysis completely in that analysis. The second thing would be to evaluate the greenhouse gas emissions. You must determine the full greenhouse gas output for all routes from the basic starting material, not just about your own reaction in your industry, but you have to go back, even if somebody has done, you must include all of it because all of it energy has gone into the product. And use this output as a new metric to evaluate a synthetic procedure in addition to the traditional approaches such as PMI, yield, number of steps, cost. These are the ones which are normally used to look at the success of the reactions. And minimize the environmental impact, invent chemistry that enables short preparation of drug substances with minimal greenhouse emissions. These are the three principles we need to add to the green chemistry so that we have a complete way to sustainability. So the first rule, understanding the supply chain, most of us say it is obtained from commercially available starting materials. That is even in newspaper, even in recent papers we write like that, but that has to change. We need to see what are the starting materials that can be prepared in a cheaper, safe and green manner. And the second one, the greenhouse gas emissions provides a metrics by which we have to measure our activities. The classical metrics of organic chemistry, like steps, overall yield, they are not applicable here now anymore. These metrics do not capture what is mandatory for chemists to deliver, achieving the required decarbonization. Now, we need to generate an agreed system that allows the calculation of carbon dioxide footprint with relative ease in a global manner. The third rule is environmental impact, and we all know about the importance of that. I don't have to elaborate on that. Now, organic chemists do synthesis, develop and demonstrate their creativity, inventiveness, and persistence. In the history of organic chemistry, there have been some fantastic synthesis, challenging structures. Now, we need to bring back the same kind of creativity and originality in the new regime, that is, how to use bio-based products and create the materials that what we require. So, we must invent chemistry that does not exist and not imagine today. Not just a gradual change and improvement, but a reinvention of what is possible and necessary. Now, decarbonization is the buzzword now, and you have to change the raw material from petrol to bio-based, that is understood, and compound derived effectively from straw food, straw wood, efficient fermentation, enzymatic approaches are important, and that becomes the foundation of new chemistry. I will skip the next few of them, it's a normal one. All I must say that much of the waste generated in a process is mainly from solvents, it comes. So circular economy, we know the importance, produce, use and throw, that has to change, we have to learn to reuse. Every day about 1.3 billion tons of food is wasted and the plastic waste goes away. And all these things, they contribute to the greenhouse gas emissions, carbon dioxide, methane, etc., microplastics, we all know about that. And what is required is the recycling, the circular economy, that is important. Now, the circular economy innovation, making these things, biorefinery will come up. I think DVT has a very big project now in the proposal in the biofoundries to generate, for example, furans, which will be into, can make paraxylene, adipic acid, diones, which go into different products. They can all be obtained from biomass production. But each one of them, you need to standardize the reaction. Similarly, lignocellulose, the lignin contributes to phenols, aromatics, diacetic acid. So we can develop, we need to develop chemistry, new chemistry, to go through these chains of processes, essentially obtained from biomass materials. Similarly, cellulose can give rise to C1, C2, C3, C4, C5, C6 chemicals, which become raw materials. I will only show one or two examples before I wind up how this can be done. This is about ibuprofen, which was made by 6 steps, original synthesis, which involves several steps and generates a lot of waste, aluminum salt waste is generated. And in today's consumption, this will come to about 40,000 tons of waste is generated. Now, this has been very, very nicely boots and X. They have shortened this thing by using acetaldehyde as a catalyst and 3 steps for 2 catalyst steps. And that is sold as a racemate, so it doesn't require resolution. Now, what this process is that the first step, the hydrochloric HF is used as a solvent and catalyst is recycled and reused. And the byproduct is acetic acid. Atom economy is higher and it reduces the waste generation and it provides an environmental impact. So these kinds of quantum chemistry innovation things to be done. The last example I am going to show you is about molnupiravir, which was during COVID time, which became a very hot molecule. It's an antiviral, and that was being prepared in 10 chemical steps, starting from uracil, then glycosylation to uridine, etc. And Now this has been replaced essentially to 3 steps by biocatalysis, starting from ribose, not from the base, but from the ribose, and used enzymatically to attack the uridine, and then through a single step process. And this has given a lot of multi-enzyme cascade, integration of ribose into acid, dynamic crystallization. So this has helped a lot in shortening. So this becomes the foundation of new chemistry to think about available starting material, cheap, and then create chemistry rather than keeping the target and generate the chemistry. Now the product life cycle, and I will skip this slide. I could talk to that anybody who is interested. Now replacement of solvent is becoming a very, very big. As I said, solvent is the main waste. And how do you replace a solvent? When did we invent the last solvent? We can ask about that. Now there are databases in which all solvents, about some 25, 30 properties of solvents have been put into that, including the green application. And now industry use this kind of things by the AI method to find out what could be your ideal solvent. Just an example. So the change of raw material basis from petrol to biomass is important. This is my last slide. One is, what is the take-home result for funding and financial agencies? When projects submitted, there was demand novel approaches. Scientists must provide metrics of minimized carbon footprint for the whole schemes for the manufacturing thing rather than just for one step. We must ask for research which addresses technologies for API production using the 3 principles that we elaborated: supply chain, greenhouse, and environmental impact. We need to add to this green chemistry. Define a globally accepted and uniform system to measure carbon dioxide emission in order to enable a strict application of these metrics, and provide incentive to have the lowest carbon footprint technologies known and used. Chemical education industry, they must bridge the gap in teaching and practice of organic process research and development. And the technical challenges requires innovation at the highest level, original and innovative chemistry for delivering solutions. Chemical community has the skills to rise to the challenge and come with solutions that we cannot even imagine today. Most important thing is, as it was said, we cannot use the next generation's future resources. Healthy life on Earth through sustainable and limited resources is most important for the future. With this thing, I thank you for your kind attention. And we just published this paper elaborating some of what I said. And I also saw that the Ministry of Chemical and Fertilizers did an excellent final report on these innovative and cost-effective technologies for manufacture of not only APIs but also for the chemicals. It's a very beautiful document which gives a lot of data. So with this thing, thanks for the attention.